Inside a black hole lies a mystery. What happens at its center? The same mystery applies to the Big Bang. Einstein's theory of gravity seems to give way, predicting the existence of a singularity, a point of infinite density, curvature, and pressure. When the entire observable universe is squeezed into a space far smaller than an atom, new physics is needed, taking account of both gravity and the strange microscopic world of the quantum. We need a quantum theory of gravity. One of the leading candidates is loop quantum gravity.
About the possibility to observe gravitational waves that comes from explosions from objects that were present before the bounce.
If the universe did not begin at the Big Bang, does that mean that the universe has always existed?
What about even before eons and eons before? We just don't know.
There could be a past history of the universe which is infinitely long.
An argument against an eternal universe is that we would never get to now if the past stretched back for eternity.
These arguments to me seem a little bit like the arguments that were used by neo-Kantians in the early days of general relativity to say that general relativity is absurd, because in general relativity, matter and energy curve space-time. But how could it be possible? Because you were to talk about matter and energy, one needs space-time. So how could it curve space-time? And very serious people argued this, very philosophers argued this, and I mean, we know that this is completely vacuous argument. I mean, it's not that there is space-time first and then that curves, but it's inevitable Big Bang type singularity. Now this conclusion is evaded in loop quantum cosmology. Initially the universe is contracting and it expands only after the bounce, and therefore the assumptions that they made is violated.
A new singularity theorem proposed by Aaron Wall uses concepts from thermodynamics to argue for a beginning.
Wall is assuming that some version of second law of thermodynamics is really fundamental and should be a fundamental ingredient in this series which determine whether there will be singularity or not. And I agree with that. I think that it really is something that would emerge in approximate sense, in the sense of the gravitational entropy. In the contracting branch, because the dynamics is different from Einstein's theory, a horizon develops, but it grows extremely rapidly. And in fact, therefore, the entropy really grows extremely rapidly. And as usual with black hole horizons, this entropy dominates completely the entropy of matter. Therefore, the entropy is really growing very rapidly, but then at the bounce, the geometry is such, which is non-trivial statement, is such that...
And that you have some atoms of space like you have atoms in a crystal.
If loop quantum gravity predicts the existence of space-time atoms, where do the new atoms come from when the universe expands?
Well, that's the same question as asking in classical general relativity. The universe expands and the volume increases. So we can just ask the question, what creates this volume? Well, it's dynamics which creates this volume. So there is no conservation law for volume, and there is no conservation law for the number of atoms of geometry.
Another route to exploring experimental testing of the theory comes from nature's most mysterious objects, black holes.
A few years back, we have detected for the first time gravitational waves directly, thanks to the LIGO antennas in the US and the Virgo antenna in Europe. And what we are basically seeing is the coalescence, the merging of two black holes, and then the relaxation of the big black hole coming from that. And the way this big black hole is losing its energy through gravitational waves might depend on quantum gravity corrections. So it is still speculative at this stage, but it is possible.
It is in fact just the continuation of a previous phase in which there is a contraction and then an expansion.
As you evolve back in time, one reaches a point of maximum density.
So this is what we call a bounce. The universe collapses and bounces back.
One of the problems of Bujold's work was that the bounce could occur when the density